Hello students, you are welcome again to MTH102 class. Today we are going to consider continuity of functions. And when we are looking at continuity of function, we are going to talk about the definition of continuity of function from layman point of view. Then where we are going to consider jump or hope or holes in a diagram. Then we use diagram to illustrate our layman definitions of continuity. Then we are now moved to redefinition of continuity, where we are going to use limits of function to define continuity of function. More also, we are going to solve the problem on continuity of function and determine whether a function is continuous over an interval or is not continuous over an interval. See, then we shall see in the class. Thank you for listening. Hello, my name is Dr. Akim Bidisu. I'll be taking you on continuity of function. If you look at my left hand side, you see a curve, a real life curve. That is a real life curve that is continuous. Mathematically, we shall define what we call continuum curve or graph or function. Let's continue in the next. Continuity of functions. We are saying the two graphs are continuous over a real number. A real number we have is minus infinity to infinity. We can see that it's continuous. And if you trace this graph like this, we trace it from the left to the right as we are tracing it, and there's no jump. We say the graph is what? Continuous. And let's say we also trace this graph like this from the left like this. We trace it, we trace it, we trace it, we trace it to here, and there's no hole or jump. We call this graph continuous. This is what we call layman definition of continuity of function. We say the two graphs are continuous. You can see here, we say note that there are no jumps or holes in the graph. That tells us that this what is continuous. Let me the intuitive definition of continuity. We say that a function is continuous over some intervals of the real number line if the graph can be traced. You know that we trace the two graphs in the last slide. You know we trace it. If that can be traced without lifting our hand or pen from the paper, we say that graph is continuous. If there is any point in an interval where a jump, jump is very important, where this jump or we have hole or curve, then we say the graph or the function is not continuous over the interval. Let's just illustrate what we call discontinuity of function, or a function is not continuous. Let's say this graph represents graph C. I will say it's not continuous over interval -5, 5. Look at this. If you consider this graph you are using, we have -5 here, we have 5 here. We say it's not continuous over the interval. Interval here is our x-axis here, and interval is between -5 and 5. That is, you can say s less minus 5 less or equal to x, x less or equal to 5. That's the interval. We say it's not continuous because the point x here, we are saying this point x here is part of domain. And when you see it, there's no line, there's no graph here. No graph here. That's why we say no graph here at points x is equal to 0. Do you get it? Let's say we want to trace this graph. If you start from our left like this, if we trace it like this, we trace it, we trace it, we trace it, we trace it, we trace it up to here. We know we don't leave our hand on the graph or our pen on the graph, or we use pointer this time and we did not use pointer on the graph. We say it what is continuous here. But let's say we want to move on to the second line, and before we move on to the second line, we have left our hand on the graph. That's why it's not continuous on this range. But we can see from here, if we start from here, we can move, we can trace it, trace it, trace it up to here. You can say is what is continuous here. That is where we have notes here. That is C is continuous over when you have from minus 5 to 0. This from minus 5 to 0 here, from here to here, x from here to here, this curve here, or the graph here is continuous. And if you look at it from here to here, you can see from 0 to 5 here, we can see the graph is also continuous. That's the part where the graph is what? Where the graphs are continuous. We can see that this graph is continuous here. The line is continuous here. It's also continuous here. Let's move on to an example on it. If you have this graph, we call it graph D. Graph D is not continuous over. This should be minus 5 because the range here is 5. And here we use infinity because we assume that the graph is coming from far, and it's also go to end from far. But here the picture we show is this from minus 5 to 5. That's the range of the graph. That's the interval of the graph. That is minus 5 less or equal to x, x less or equal to 5. That's the range. If now to use it now, we say D is not continuous over minus 5 to 5, because when we move, let's say when we trace, because when we trace this graph from here, we are tracing it, we are tracing it, we are tracing it, we are tracing to here. When we get as 2, there is O. There's O here, or we call it a jump. There's O here, there's O here. We have to jump this O before we continue. At this point, x is equal to 2 is not continuous. At this x is not equal to, it's not continuous. You can see it, it's not continuous. Look at it from here, also continuous. Then what we are saying here, that is, if you trace it from here to here, that is, graph D is continuous at minus 5 to 2. It's continuous at minus 5 to 2. That's what you have here. Because there is a jump between 2 to 5. And it's also continuous from 2 to 5. You can see from here. It's also continuous from here to here. It's continuous from here to here, from minus 5 to 2 here, and it's also continuous from 2 to 5, because the whole graph or the whole line is not continuous, because we have a hole here, or what we can call a jump. We also have another example of the continuity of function. We consider this graph. This is very important graph that we are using in mathematics. Look at it. We say it's not continuous over minus 5 and 5. Look at it from here to here to here. It's not continuous. But when we trace the graph from our left hand side here, we trace it up to here. That is, it continues from 5 here, exactly from minus 4 here, exactly 4 here, from minus 4 here to 1. We can say from minus 5 if it's extended from minus 5 to 1, or from what we are seeing clearly on our graph is from minus 4 to 1, that is continuous there. And from here we have a jump here. There's also a graph here, jump here. This one from 1 to 4 here is also continuous. That's where we have the two lines to be all to be continuous. Let's move on to of continuity of function. We said a function is continuous at, look at it, at point s is equal to a. A is a point. At point s is equal to a. If f of a exists, if the function of a exists, that is the output at a exists, that's the output at a exists. But if you have the limit, if the limit of f of x as s tends to a also exists, that is the limit as s tends to a exists, we can say a similar, the function is what is going to be continuous. But more importantly, the limit of f of s and s tend to a must equal to function of a, that is for f of a must equal to, because we can say this function is continuous. This last condition is the most important aspect, is the most important that we have to consider when solve the problem of continuity of function. Look at it, the limit is the same as the output. You must consider that a function is continuous over an interval I if it is continuous at each point in the interval. It has to be continuous in the interval. Let's move example. Let's determine whether the function given by f of x is equal to 2x plus 3 is continuous at the point s is equal to 4. Then to solve this problem, you copy out the question, that is f of s is equal to 2x plus 3 at s is equal to 4. Then we have to ascertain that f of a exists. The a here is 0.4. Where you have a, we put 4. Then is equal to 2x. Instead of x, we put 4. That is 2 times 4 plus 3. 2 times 4 is 8. 8 plus 3 gives us 11. That is function of 4 is equal to 11. That is the function at 0.4 exists. That is, we got that one. Function of 4, function of f as 0.4 exists. Let's check whether the limit exists. The limit of f of s as s tends to a, this will give you the limit of f of s at s tends to 4. If you put in the limit, where we have x, we put 4. That is s times 4 plus 3 will give us 11. This will as s tends or approaches 4. That one exists. Then the last one, we have to consider the function exit and the limit. And if you have here in the function of at 0.4, it gives us 11. The limit at 0.4 at s tends to 4 it also gives us 11. You can see that means the limit of f of s as s tends to 4 equal to function at 0.4 is equal to 11. Therefore, this function is continuous at point s is equal to 4. Let's move to another example. This one states that is it function of f given by this function f of s is equal to s squared minus s continuous at point s is equal to 3. Why or why not? We have to solve this. How to solve it? The first rule, you must find that function of 3 exists. Let's see, look at it. This is the formula, that is s equal to square minus 5 x squared minus 5 at x equal to 3. Then if you put where you have x, you put 3, we are going to have x squared minus 5. This one is equal to 3 squared will give us 9. 9 minus 5 gives us 4. That is the function at point x is equal to 3 exists. Then let's find the limit. The limit also f of x as x tends to 4, as x tends to 3. There's a mistake here. This should be 3. X tends to 3. We have, when we have, if you put it in the function, we have it at 3 squared minus 5 is equal to 4. You can see as x tends to 3. Then you can see the limit and the function at point x is equal to 3, it gives us 4. That shows that this function f of x is equal to x squared minus 5 continuous at point x is equal to 3. Let's look at this beautiful example. It's so unique that we have not considered something like this so far. Let's consider this points wise. Is it the limit? Is it the function g given by this continuous at point x is equal to minus 2 y and y naught? Then you copy out the function, that function g, we copied it out like this. Then don't forget the statement here has x is equal to minus 2. That you look at this, we go to this second one, that is we have x less than or equal to minus 2. We consider this first because this is where we have to find the f of x. This is where we work. That is when it's equal to minus 2. Then when g is equal to minus 2, we have for x minus 1. That is minus 2, where we have x, we put minus 1. We put minus 2. We put minus 2. We have minus 2 minus 1 is equal to 3. That's how we get this. That is g at point x is equal to minus 2 exists. Give us minus 1. That's one condition. We satisfy one condition. Let's get the second condition. You know, this one move from the left to right. We have to test what we call left limit and right limits. We have to work on left limits and right limits. To work on left limit, we have limit t of x as x tends to minus 2. You know, left, this minus means left, just indicate minus. It has no effect on it, just it means left. Then if you put it in the left, you have 1 over 2 here. 1 over 2x. This place should be x. 1 over 2 here. This place should be x. 1 over 2 here. That is 1 over 2x. Where we have x, we replace it by 2 minus 1. Minus 2 minus half times 2 will give us minus 1. We have minus 1 minus 1 is equal to minus 2. This gives us minus 2. Then let's look about the right. The right is mean this. When limit g of s as x tends to minus 2, that positive means right. Then if you consider we have s minus 1, and this will give you s instead of s, this will be s minus 1. Instead of s, we put 2. 2 minus 1. This should be minus 2 here. Minus 2 minus 1 will give you minus 2 minus 1. This will give you minus 3. This will give you minus 3. Then you can see we have the limit of left limit and right limit are not equal. And if you know, if you are previous condition for limit to exist, the left and right limit must be the same, must be equal. Since they are not the same in this case, we say g, since they are not the same, that means the limit of g of x tends to minus is not exist or does not exist. It does not exist. It means does not exist. This means the limit does not exist because the left limit must equal to right limit. Since the limit does not exist, that means g is not continuous at point x is equal to minus 1. That is taken for today's class. I want everybody to go and study this class so that we can use it to solve many problems on continuous function or continuity of function so that it will help us. Till then, everybody to attend today class activities. You can see the question given. Please solve it, work it on your own, and let me have feedback, feedback of this lesson. Please do it on your own. Don't let anybody to assist you. It's easy as ABC. Thank you for listening. Till then, bye.